Distance and scale alter the way gravity manifests. This force can be gentle around small worlds, intense near dense stars, or subtle and stretched across vast regions of space. In this video, we will explore gravity not as a single, uniform rule, but as a force that takes many forms depending on its environment, from planets and moons to stars, galaxies, and even the empty spaces between them. This is a slow journey, meant to feel how gravity forms and shapes the universe. There is no rush, no need to grasp everything at once, just a calm exploration of a force that seems simple up close, but whose complexity quietly grows as we move farther out. Gravity is often experienced long before we give it a name. It is present in every footstep touching the ground, in the way objects fall when released, in the quiet certainty that things tend to stay put unless acted upon. There are no vibrations, no sound, no visual signals. Instead, gravity feels like the default state of existence, so ingrained that it becomes invisible, blending into the background of perception. On Earth, gravity gives the body weight, pressing down in every moment and creating resistance that muscles learn to counter from the very first steps. Standing, walking, sitting, lifting, or resting, all are shaped by this patient pull. It almost never turns off, and so rarely draws attention, like air pressure or the flow of time. Gravity only becomes noticeable in its absence, or when something goes wrong. An object falls, a glass slips from the hand and shatters on the floor. Those moments feel inevitable, as if they could not have been otherwise. Over time, the human mind stops questioning them. Gravity becomes familiar and expected, present as an unchanging law. Indoors or outdoors, near sea level or on a low hill, gravity feels uniform. A cup weighs the same in the kitchen as it does in the garden. The body does not feel lighter or heavier from moment to moment. From a human perspective, gravity seems fixed, almost absolute. Yet even on Earth, gravity is not perfectly uniform. Its strength varies slightly with location, weaker at the equator than at the poles due to Earth's rotation and slightly flattened shape. Altitude also matters. On a mountain, gravity is slightly weaker than at sea level because the distance to Earth's center increases. These differences are small, below human perception, but can be measured with sensitive instruments. Gravity feels stable to us not because it truly is, but because human perception is limited. These subtle variations are masked by the scale of everyday life. Muscles, bones, and the balance system adapt to the local gravitational environment and treat it as normal. Over time, this normal becomes invisible. Historically, understanding of gravity shows that humans initially did not perceive it as an invisible foundation, but as a force acting between objects. In the late 17th century, Isaac Newton described gravity as a universal attraction between all masses. Every object with mass pulls on every other. The pull is stronger for heavier objects and weaker over greater distances. This idea explained why objects fall, how planets move, and the moon's orbit. Newton revolutionized thought by linking phenomena on Earth with motion in the sky. The same force that causes an apple to fall also keeps the moon orbiting Earth, shaping the paths of planets around the Sunday. Gravity was no longer a local phenomenon. It became universal, operating throughout the cosmos. For centuries, Newton's theory of gravity provided accurate predictions for most situations in daily life and astronomy. It explained why objects accelerate uniformly near Earth's surface and why planets follow stable, repeating orbits. In practice, the theory works extremely well and remains valid in many contexts today. However, Newton also reinforced the idea that gravity behaves uniformly everywhere. Even though the equations allow for variations in strength, the underlying picture still suggests a single rule applied evenly across space. Gravity, the phenomenon we often call a constant of the universe, is actually only a local expression, a perspective from Earth. This medium-sized rocky planet, with its particular mass, radius, and internal structure, generates a force strong enough to hold the atmosphere, shape the oceans, and anchor life to its surface. yet light enough for movement to remain easy and biological structures to stay stable. This balance feels natural only because life evolved in this environment. If Earth were slightly more massive, everything would weigh more. Each step would become more laborious, and biological structures would need to be sturdier to withstand the force. If Earth were lighter, objects would fall more slowly, jumps would reach higher, and the atmosphere could thin or escape into space. Small changes in planetary mass lead to noticeable differences in gravitational experience, and because Earth provides a narrow, stable range, humans easily mistake this local balance for a universal standard. Gravity seems unchanging because it has always been stable within the limits of human experience. But those limits are tiny compared to the diversity of environments across the universe. Even within the solar system, gravity varies significantly. The Moon's gravity is weaker than Earth's, allowing astronauts to lift their bodies easily and objects to follow gentle arcs. Jupiter's gravity is many times stronger, compressing dense matter and dominating the motion of surrounding objects. These differences require no new laws. They arise naturally from variations in mass and size. The key point is that gravity does not exist at a fixed strength everywhere. It depends on the properties of objects, their mass, distance, and distribution. Gravity on Earth is the result of this specific combination, not a default setting of the universe. Viewing gravity as a local experience opens a new door. Curiosity about how this force behaves elsewhere, under different conditions, and on different scales. The familiar pull downward becomes just one example among many possibilities, rather than the sole definition. From the obvious and reliable, we can begin to gently question our assumptions. Gravity does not change abruptly from place to place, but it varies meaningfully. The version on Earth is not wrong or deficient, it is specific. Belonging to this planet, at this distance from its center, with the mass distributed beneath the surface. Recognizing this does not make gravity less trustworthy. On the contrary, it situates the force within context, part of a broader pattern stretching far beyond the ground beneath your feet. Gravity is often described as a force pulling objects together across empty space. This description suffices for many everyday situations, but modern physics understands it differently. It is not a mechanical force, not an invisible string connecting objects, but a fundamental interaction arising from the structure of the universe. Unlike familiar forces when a hand pushes a door, there is contact. When a magnet attracts metal, the interaction weakens with distance. Gravity is different. It acts between all objects regardless of distance, cannot be blocked, turned off, or shielded, and extends across space, shaping the motion of planets, stars, and even galaxies. For centuries, gravity was described through the lens of Isaac Newton, an attractive force between objects. With mass, the greater the mass, the stronger the force, the farther apart, the weaker the pull. This description is simple, intuitive, yet remarkably effective. It explains why objects fall, why planets follow orbits, and why the moon and comets move predictably. Even today, Newton's formulas remain sufficiently accurate for engineering, spaceflight, and many practical applications. However, Newton only described how gravity behaves, not its true nature. The force was considered instantaneous, acting across empty space with no clear mechanism. As scientific understanding progressed, this limitation became increasingly apparent. In the early 20th century, Albert Einstein offered a completely new perspective. Gravity was no longer a force pulling through space. It was the consequence of the geometry of spacetime. Space and time are no longer separate backgrounds but merge into a single physical structure called spacetime. Spacetime can stretch, compress, and bend. Mass and energy shape its curvature, and that curvature guides the motion of objects. Under general relativity, objects fall not because they are pulled, but because they follow the straightest possible paths in curved spacetime known as geodesics. To an observer within spacetime, this motion appears as acceleration, producing the sensation of a downward pull. The effect goes beyond motion. Gravity influences time itself. Clocks near massive objects run slower, while clocks farther away run faster. This effect has been measured with atomic clocks and must be accounted for in satellite navigation systems to maintain accuracy. The difference between Newton and Einstein is not a matter of right or wrong. Newton is an approximation, sufficient when gravity is weak and speeds are low. General relativity becomes essential when gravity is strong, distances are large, or precision is critical. On Earth, the differences are subtle. Everyday experience does not reveal the curvature of spacetime. Objects still fall, orbits remain stable, and gravity as a force remains intuitive and easy to grasp. But beneath this familiar appearance lies a deeper structure. Spacetime is not passive, it reacts to mass and energy. Earth curves the surrounding spacetime, and objects move naturally along these curves. The Moon follows a curved orbit around Earth, not because it is pulled sideways, but because it moves within the geometry of spacetime created by Earth. The key point is that gravity is not something added to space, it is embedded in the very shape of spacetime. Where spacetime is more curved, gravity is stronger. Where it is flatter, gravity is weaker. This explains why gravity differs from other forces. There is no substance flowing between objects, no particle carrying the force. Instead, a continuous geometric structure governs motion everywhere, and objects respond simply by existing within it. Imagine motion without gravity. In empty, flat spacetime, an object moves uniformly in a straight line at a constant speed, the natural state of motion. Gravity changes this concept of straight by curving the very geometry through which the object moves. What we perceive as curved motion or acceleration is actually straight motion in curved spacetime. This also explains why gravity cannot be switched off. As long as there is mass and energy, spacetime has structure, and as long as spacetime has structure, motion is guided by it. Gravity is not an overlay added to the universe. It is woven into the very geometric nature of the cosmos. General relativity also predicts effects that Newton could not. Light bends around massive objects, and planetary orbits precess phenomena that have been observed and confirmed. It emphasizes that gravity must be understood as geometry, not as a force. Though abstract, this perspective does not contradict everyday experience. Gravity on Earth remains stable and uniform, while elsewhere, it can vary significantly. Near extremely massive objects, spacetime curves violently, producing effects far beyond Newton's predictions. In regions lacking matter, spacetime is nearly flat, and gravity is faint. Shifting from the image of force to geometry makes gravity both simple and profound. Simple, because there is no mysterious action at a distance. Profound, because it unites space, time, motion, and mass within a single framework. Familiar experiences wait. Falling objects, planetary motion remain intact. What changes is the explanation behind them. Gravity is not a force acting in the universe. It is part of the universe itself. Gravity varies because the universe is not uniform. Objects differ in mass, location, and distance. These differences matter. They determine the strength of gravity and how it is experienced from one place to another. On Earth, the sense of stability results from specific local conditions, not a universal standard. At a fundamental level, gravity depends on two factors: mass and distance. Greater mass, stronger force. Greater distance, weaker force. This principle holds in Newtonian terms. Force increases with mass and decreases rapidly with distance. Even in the more profound space-time-based explanation, the relationship between mass, distance, and strength remains observable. On Earth, everyday movements change the distance to the planet's center only slightly. Standing, sitting, or walking alters it minimally. Because Earth's mass is large and distance variations are small, gravity feels constant. As distance increases, gravity gradually weakens. It does not disappear abruptly, just diminishes progressively. For example, the Moon remains in orbit around Earth, hundreds of thousands of kilometers away, because gravity is strong enough to hold it, yet weaker than at Earth's surface. At that distance, Earth's pull is still strong enough to keep the Moon in orbit, even though it is much weaker than on the planet's surface, and the Moon responds with its own gravity, raising and lowering Earth's oceans in the rhythm of the tides. The two celestial bodies pull on each other across empty space, demonstrating that gravity requires no contact, no intermediary. It extends far, very far. The farther one moves away, the weaker Earth's influence becomes. By the time you reach the distance of the Sun, Earth's pull is tiny, almost negligible compared to the enormous mass of the central star. The Sun, with its overwhelming mass, governs the motion of all planets, asteroids, and comets in the solar system. Earth is now just a tiny component among countless other objects. The same pattern repeats at every scale throughout the universe. Small bodies like asteroids exert only a faint pull. Planets are stronger, stars are stronger still, and entire galaxies, each containing billions of stars, generate gravitational forces large enough to shape even vast regions of space. The most remarkable aspect is that gravity never disappears abruptly. There is no boundary beyond which it simply ceases. It diminishes smoothly and continuously with distance, following the inverse square law. Even two objects, billions of light-years apart still, in theory, exert a slight pull on each other. This effect may be negligible in practice, but it is never exactly zero. It is this infinite, unbounded reach that is difficult for us to grasp. Human intuition is accustomed to forces with clear limits. A push or a pull ends when contact ends. Gravity is different. It reaches out forever, gradually thinning and weakening, but never fully vanishing. To describe this phenomenon, physicists use the concept of a gravitational field. It is not a substance filling space, but a way of expressing that at every point in space there is a certain strength and direction of attraction, determined by the mass and position of all surrounding objects. Near a massive body, the gravitational field is strong and intense. Farther away, it weakens and spreads out. When multiple objects are present, their fields overlap and combine, producing complex patterns. The force you feel at any location is the sum of all these fields. On Earth's surface, the gravitational field is almost entirely due to the planet itself. Contributions from the Moon, Sun, or distant planets are minor, detectable only with extremely sensitive instruments. For this reason, our everyday experience of gravity feels simple and unified. But as we move away from Earth, the balance changes. On the Moon, Earth's field is still present, competing with the weaker field of the satellite itself. In deep space, far from all massive bodies, gravitational fields become faint and diffuse. Motion there is guided by whichever mass, even a small one, is strong enough to dominate over others. From the perspective of general relativity, all these variations are manifestations of spacetime curvature. Mass and energy bend the surrounding space. Near a massive object, curvature is strong, and paths are noticeably deflected. Farther away, curvature softens, and space gradually flattens. This transition is smooth and continuous, with no abrupt jumps, exactly the way gravity truly operates. Gravity is never uniform throughout the universe. Objects with different masses are arranged in complex patterns, each location with its own balance. Even within a planetary system, the rocky surfaces of terrestrial planets, the atmospheric layers of gas giants, and the space between planets all create distinct gravitational conditions. These differences shape how matter behaves, how objects move, and how structures form over time. A subtle but important consequence is that gravity is always local. It arises from the surrounding objects and the distances to them. The gravity you feel is not a constant, imposed from outside. It is the result of the universe around you, acting through mass, distance, and geometry. This locality explains why gravity feels reliable, yet can still vary. Anywhere in the universe, the gravitational environment changes gradually. Massive objects move over long timescales, and distances shift slowly. As a result, gravity may appear stable within a local reference frame, even while differing widely across regions. Understanding gravity as something that varies with mass and distance connects familiar experiences with the vast universe. The steady pull you feel on Earth is neither exceptional nor the sole law, it is just one of many possible outcomes. The same physical principles apply everywhere, but the effects differ depending on location and the objects involved. Gravity does not behave differently because the laws of physics change. It behaves differently because the universe is not uniform. On Earth, the planet's surface provides a basis for human intuition. Objects fall consistently, and the body has a moderate weight, not so heavy as to crush, not so light as to feel insensible. Earth's mass and radius generate the gravity to which life has adapted over billions of years. Muscles, bones, circulation, and the balance system all have adjusted to this specific gravitational environment, making it feel natural and normal. The Moon presents the first obvious contrast. Its mass and radius are much smaller than Earth's, and surface gravity is weaker. An object weighing 100 kilograms on Earth weighs only about 16 kilograms on the Moon. Astronauts immediately experience this difference. Movements are slower, jumps are higher. Each step becomes a graceful bound. The weak gravity is not just due to the Moon's small size, but also reflects its internal structure. It is less dense than Earth, with a small metallic core and a simple geological history. Small mass within a small volume creates a weak surface gravitational field light enough to alter motion without eliminating it entirely. Mars presents a different variation. Larger than the Moon but smaller than Earth, surface gravity is intermediate. A person standing on Mars would weigh about 1/3 of their weight on Earth. This difference is enough to affect movement and long-term health, but not so extreme as to make locomotion unfamiliar. Mars also illustrates the importance of composition. Although larger than the Moon, it is less dense than Earth, with a relatively small core compared to its size and a total mass lower than its diameter might suggest. Gravity is not a fixed force, and its variation across the universe is evident. Each location in the universe has its own unique influence from nearby objects, creating a distinctive gravitational environment. The universe, with countless objects of varying masses and structures, cannot have a uniform gravitational force. Each region of space is governed by factors such as mass and the distance between objects. Even within a planetary system, gravity changes dramatically. Earth, a rocky planet with significant mass and radius, has strong and stable gravity. This has been a fundamental factor for life and the development of the human body over billions of years. Every human activity, from bodily movement to the stability of the musculoskeletal system, depends on a specific level of gravity. In contrast, the Moon, although much smaller than Earth, has much weaker gravity, with less mass and a smaller radius. The Moon's gravity is only about 1/6 of Earth's, causing astronauts' steps to become slow jumps, and objects falling to the ground take longer to land. This difference is not only due to mass, but also related to the internal structure of each planet. The Moon, with its low density and smaller metal core, produces much weaker gravity. In contrast, Mars, although having more mass than the Moon, is smaller than Earth and has a lower density, resulting in moderate gravity, about 1/3 of Earth's gravity. This means that the gravity on Mars is not too light, but it is enough to impact human movement and long-term health. Each planet and moon has its own distinct characteristics, from density and composition to core structure. Gravity at each location varies not only because of size, but also due to deeper factors like density and mass distribution. Earth serves as the benchmark for the gravity we feel, but other places like the Moon and Mars offer completely different gravitational experiences. From this, we understand that gravity is not an immutable law, but rather the result of specific factors at each point in the universe. On Mars, gravity remains moderate, lighter than Earth, but enough to maintain a sense of stability. Data from NASA missions such as Viking, Mars exploration rovers, Curiosity, and Perseverance have confirmed the accuracy of theoretical calculations about the gravity of this planet. On the surface of Mars, objects fall slower and jumps become higher and longer. the body will gradually adapt to the reduced load on the bones and muscles. These changes are not just hypotheses. Studies on astronauts living aboard the space station have provided insights into how gravity affects the body and human movement. Meanwhile, gas giants offer surprising conditions. Jupiter, the largest planet in the solar system, has a surface gravity stronger than Earth's. Although it lacks a solid surface like other planets, at its cloud layer, gravity is even twice as strong as Earth's. A person standing there would feel much heavier, even though Jupiter is primarily made of hydrogen and helium gas. This is due to Jupiter's massive size. Despite having a lower density than Earth, its immense size contains an enormous amount of material in a vast space, generating an incredibly powerful gravitational field that spreads far into space. Saturn, although nearly as large as Jupiter, has weaker surface gravity due to its much lower density. Density and mass distribution play a much more significant role than size alone when determining a planet's gravitational strength. This shows that a planet could be larger but still have weaker gravity if its mass is more evenly distributed. The differences in gravity between planets help us understand how each world can provide a different sensory experience. The Moon, with its weak gravity, gives a light and easy feeling for movement. In contrast, on Mars, gravity is reduced, but still provides a sense of familiarity. Near the clouds of Jupiter, gravity is so powerful that every movement becomes much harder. None of these experiences change the laws of physics. They are natural outcomes of how mass is distributed. NASA missions like Juno around Jupiter and the Lunar Reconnaissance Orbiter around the Moon have provided crucial data, helping to identify small variations in gravity due to the internal structures of the planets and mass distribution. These differences not only occur between planets, but even on the surface of a single planet, where geological structures, crust density, and geological history create subtle but noticeable changes in gravity. Through these examples, we can see that gravity depends not only on size but also on the density and internal structure of a planet. Planets of similar size can have dramatically different gravity. Gravity is a factor highly sensitive to what lies beneath the planet's surface, not just what we can see from space. These discoveries make gravity no longer an abstract concept in physical equations, but a phenomenon that can be directly felt and compared across the planets in our solar system. Under the stable light of a star, gravity exhibits a much stronger and more complex force compared to that of solid planets. Inside a star, gravity not only acts on the surface but spreads throughout its entire volume, from the center outwards. A star begins as a cloud of gas and dust, pulled together by gravitational forces. As the material accumulates, gravity becomes stronger, pulling more material toward the center of the star. This compression increases the temperature and triggers the process of nuclear fusion. Gravity does not disappear when this process begins. Instead, it becomes part of a delicate balance. Gravity pulls material inward, while the energy from nuclear fusion creates heat and pressure that pushes outward. The balance between these two forces, known as hydrostatic equilibrium, keeps the star shining steadily for millions or even billions of years without collapsing or disintegrating. However, this balance is not fixed, but rather a dynamic process, maintained moment by moment. As the star's core contracts, the temperature increases, nuclear fusion becomes more intense, and the outward pressure also rises to restore balance. When the star's core expands, the temperature drops, the fusion process slows down, and gravity once again takes control. This self-regulating process ensures that stars remain stable over long periods. The strength of gravity in a star depends heavily on its mass. Stars with larger masses have stronger gravity, which increases the core temperature and accelerates nuclear fusion. As a result, large stars burn fuel faster, shine brighter, but have shorter lifespans, undergoing extreme conditions inside. In contrast, smaller stars, like our Sun, have strong enough gravity to maintain fusion, but not enough to make it happen quickly. Our Sun has a core temperature of around 15 million degrees Celsius, enough to fuse hydrogen into helium at a steady pace. This stability helps the Sun maintain a steady shine for billions of years, providing a long enough period for life to develop on nearby planets. Gravity inside stars also determines how energy moves outward. In some regions, energy is transported by radiation, with photons being scattered continuously as they move outward. In other regions, energy is transported through convection, as hot plasma rises and cooler material sinks. The structure of the layers within a star is determined by the interaction between gravity, pressure, and temperature. Studies on solar physics have helped us understand this internal structure better. Research like helioseismology, which studies oscillations on the Sun's surface, allows scientists to indirectly study the internal structure. By measuring waves traveling through the Sun, researchers can infer the density, temperature, and movement beneath the visible surface. Data obtained from missions like SOHO, Solar and Heliospheric Observatory, and SDO, Solar Dynamics Observatory, have further clarified this picture. Observing solar oscillations, magnetic fields, and the energy emitted from the Sun all show that gravity is the deciding factor in the structure and stability of a star. Without gravity, the nuclear fusion process could not be sustained, and the material in the star would scatter into space. Without fusion, gravity would cause the star to collapse. The balance between gravity and nuclear fusion is not permanent. As a star ages and its fuel runs out, gravity gradually takes over. When the hydrogen in the core is exhausted, the nuclear fusion process will slow down, the outward pressure will weaken, and gravity will contract the core, increasing the temperature until a new fusion process can begin, if possible. Ultimately, for stars with large masses, gravity will take complete control when the nuclear fusion process is no longer strong enough to create the necessary pressure. The star's core will collapse rapidly, leading to dramatic events like a supernova explosion. Even in dramatic moments, gravity remains central, controlling the process of collapse, recovery, and the formation of dense remnants. Notably, gravity in stars is not just about pulling matter inward, but also plays a crucial role in creating the necessary conditions for energy production, maintaining stability, and determining the star's lifespan. Gravity acts as the internal architect, shaping the star from the inside out rather than only operating on the surface. This perspective expands the role of gravity beyond what we perceive on solid planets. On planets, gravity defines weight and structure, but in stars, gravity adjusts balance, transformation, and long-term change. This interaction not only keeps us grounded on Earth, but also helps stars shine steadily across galaxies. Understanding gravity in stars highlights its flexibility. Gravity can adapt to different forms of matter, from solid rock to hot plasma, yet always follows the same basic principles. This continuity allows gravity to function across a vast range of environments without encountering any contradictions. When we recognize gravity as an internal organizing force, the behavior of stars becomes much easier to comprehend. The stability, brightness, and evolution of stars are all the natural results of the balance between inward gravitational pull and outward energy. Gravity not only affects stars but also defines what constitutes the existence of that star. However, not all objects in the solar system have enough mass for gravity to clearly govern their behavior. Apart from large planets and moons, there exists a group of smaller objects where gravity operates at its weakest. Asteroids, comets, and small moons are prime examples of a world where gravity is present but not strong enough, creating an environment where the sensation of being unbound is common. On these objects, gravity is often described as microgravity. This does not mean that gravity does not exist, but rather that the gravitational force at their surface is extremely weak compared to Earth. On some asteroids, surface gravity can be so weak that it is tens of thousands of times weaker than Earth's. A slight push can send an object drifting at walking speed and never return. This weakness in gravity results from the limited mass combined with small size. Many asteroids are only a few kilometers long, and some are even much smaller. Although they may be composed of rock or metal, There is not enough mass concentrated at a point to create a strong gravitational field. As a result, it is a world where weight is hardly felt. Comets share similar characteristics, although they have a different composition. Often described as icy rubble piles, comets are a mixture of icy gas, dust, and rock, loosely held together. Their gravity is so weak that material can easily escape. When heated by the Sunday streams of gas and dust ejected create tails, stretching millions of kilometers through space. Gravity tries to hold the comet together, but the heat from the sun usually overpowers gravity, causing it to fail in keeping the material. Small moons orbiting planets also illustrate this weakness. Some moons of Mars and outer planets have irregular shapes and weak binding. Their gravity is strong enough to keep them intact under quiet conditions, but not strong enough to form a spherical shape. They retain elongated or lumpy shapes, reflecting their weak intrinsic gravitational force. On small objects in space, gravity operates in a very different way. While on Earth, gravity facilitates phenomena like landslides, erosion, and the accumulation of material. On asteroids and comets, gravity is so weak that materials cannot flow downhill as they do on Earth. In fact, even a slight disturbance can cause dust to float into space instead of falling to the ground. Surface features, such as impact craters, remain unchanged over long periods because erosion virtually does not occur. These characteristics have been clearly confirmed through space missions. Japan's Hayabusa mission visited the asteroid Itokawa and discovered that its surface was not solid rock, but a loose pile of gravel, held together only by weak gravity. This confirmed the long-held theory that many asteroids are not solid blocks of rock but rather loose structures made up of small debris. Similarly, the European Space Agency's Rosetta mission provided a clear view of the gravity of comets when it observed and eventually landed on the comet 67P, Churyumov-Gerasimenko. Rosetta showed just how weak gravity can be. When it landed, the lander was bounced back because gravity was too weak to hold it in place. The landing system struggled because even small mechanical forces could make the lander escape the comet's pull. These missions have revealed an important truth. Weak gravity allows objects to exist in a state that would be impossible on larger planets. Materials may remain exposed, cavities may persist without collapsing, and internal structures may be fragile, but still stable over time, due to the rarity of external impacts. Gravity in these environments also alters the internal structure of small objects. Without strong compression, the material inside remains porous, with voids still present and density unevenly distributed. These features affect how these objects respond to impacts, heating, and tidal forces from nearby planets. However, gravity still plays a crucial role. It determines whether material escapes into space or returns, and it controls orbital movement and the long-term stability of the object. Gravity defines the boundary between what remains part of the object and what drifts into space. The difference here is a matter of strength, not the presence or absence of gravity. When comparing small objects with planets, we see that gravity on planets governs structure and movement, while on small objects, gravity is just one of many factors influencing their behavior. These small objects are caught between aggregation and dispersion, where gravity is just strong enough to organize the material but not strong enough to impose order. Understanding gravity around small objects completes the picture of variation within a single system. From the immense gravity in stars to the weak pull of an asteroid, the same fundamental interaction operates across a vast range of strength. Gravity does not disappear as objects become smaller. It simply becomes quieter, more subtle, and easily overlooked. When looking at orbits, it often feels counterintuitive because it contrasts with everyday experiences. Objects dropped will fall straight down. Objects thrown will fall after some time, but in space, they are deeply interconnected. An orbit is not an escape from gravity. It is an object that is always falling without ever touching the ground. This idea was clearly explained by Isaac Newton through a simple thought experiment known as Newton's cannon. Imagine a cannon placed on a very high mountain, beyond the atmosphere. If a light cannonball is fired, it will fall not far from the base of the mountain. If fired stronger, it will travel further before falling. If the speed is increased enough, the cannonball will orbit the planet, falling toward Earth but never actually touching it. At this point, the cannonball will be in orbit. The important thing here is that gravity always pulls the cannonball downward. What changes is its forward motion. When the forward speed is high enough, the surface of the planet curves beneath the falling cannonball. The cannonball is always falling, but the ground is falling at the same rate. As a result, it will have a stable orbit around the planet. In space, an orbit is not a state of escaping gravity but rather a delicate balance between motion and gravitational force. Contrary to the common misunderstanding of zero gravity, the reality is that gravity is always present in space. For example, in low Earth orbit, gravity is only slightly weaker than on Earth's surface, and the International Space Station still experiences nearly 90% of Earth's gravity. However, everything there feels weightless. This leads to one of the biggest misconceptions in space science. Astronauts do not float because gravity doesn't exist, but because there is no support force beneath them. Gravity is not the same as weight. Weight occurs when gravity is counteracted by a surface. On Earth, the ground pushes back as gravity pulls down, creating the sensation of weight. In orbit, no surface provides an upward force, so everything, from astronauts to spacecraft, falls together under the influence of gravity. Because all objects fall at the same rate, there is no relative motion between objects in the spacecraft. Tools float, bodies drift, and liquids form into spheres. This state is more accurately called microgravity or free fall, rather than zero gravity. The weightlessness feeling comes from the continuous falling, not because gravity doesn't exist. This concept aligns with our modern understanding of gravity as a curvature of space-time. In curved space, objects move along their natural paths unless another force acts on them. A spacecraft orbiting Earth follows such a trajectory. Gravity does not pull objects toward the center like a rope, but guides their motion. Seen this way, orbit is not a battle against gravity, but a passive response to it. Spacecraft do not need to continuously push to maintain their orbit. Once placed on the correct path, the spacecraft will automatically follow it, shaped by Earth's mass and the curvature of the surrounding spacetime. This also explains why orbits can exist around many different objects. Moons orbit planets, planets orbit stars, and stars orbit the center of galaxies. In each case, gravity creates curvature and motion that help objects travel along stable paths through the curved space around them. Distance plays an important role in shaping these paths. Orbits closer to the object require higher speeds to avoid falling inward. Farther orbits require slower speeds because gravity is weaker. These relationships can be calculated precisely, but the basic idea is simple. An orbit is continuous falling, guided by gravity. This idea may feel counterintuitive because falling is usually associated with impact. On Earth, falling objects quickly hit the ground, but in orbit, the scale is different. The curvature of the planet becomes part of the motion. The fall continues indefinitely without impact, as long as the path remains clear. This understanding helps resolve many common misunderstandings. Satellites do not hover over Earth. They are not held by outward forces. They are moving fast enough that their fall becomes a curve rather than a straight drop. This scenario also explains why orbits can decay. Even the thin atmosphere exerts friction that slightly slows objects. Their forward speed decreases, and the balance shifts. The curve steepens, and the object eventually returns to the atmosphere. Gravity remains unchanged. What changes is the motion. When viewing orbit as continuous falling, gravity becomes less mysterious and more refined. Gravity is not a simple downward pull that must be overcome. It shapes the paths that objects naturally follow in space. Motion and gravity work together, creating stability without stillness. This understanding clarifies that gravity is a guide, not a constraint. It allows objects to move freely while still being bound. The orbits of objects in space are not an escape from gravity but a continuous fall, guided by the curvature of the world beneath them. Outer space is often imagined as a place where gravity disappears, where distance gradually weakens its influence until nothing remains significant. When stars fade and galaxies drift into the dark, it's easy to think that gravity must be so weak that it no longer exists. However, in reality, gravity does not vanish in empty space. It only becomes gentler, more diffuse, and harder to notice, but it never completely disappears. What changes as we move away from stars and galaxies is not that gravity ceases to exist, but how it manifests. In dense environments, gravity is very clear. Objects fall, orbits become tighter, and movement bends in a clear manner. In sparse environments, gravity still operates, but its effect unfolds slowly, stretching across vast distances and over long periods. The lack of nearby matter does not eliminate gravity. It only reduces its intensity over short periods. Gravity does not need nearby objects to function. Every object with mass contributes to the fabric of spacetime, and this contribution stretches infinitely. The influence of gravity weakens with distance, but it never stops. A star can influence spacetime far beyond its light's reach. A galaxy creates an impact on the motion of objects even at the outermost edge of its light. Even when no clear force source is nearby, gravity still reflects the combined influence of distant masses. Interstellar space is a useful example of this. Between stars, the distances are vast, yet gravity still operates. Stars within a galaxy do not drift alone in space. They orbit a common center, governed by the combined gravitational field of billions of stars, gas clouds, and invisible matter. At every point between stars, gravity is the result of the interplay of these influences. No single object dominates, but all of them together create the manner in which motion occurs. The space between galaxies further extends this idea. Between galaxies, matter is very sparse. Light may travel millions of years without encountering a single star, yet galaxies still move in a structured way. They drift toward galaxy clusters, tracing long threads and avoiding vast empty areas called cosmic voids. These patterns are not because gravity is absent in empty space, but because gravity has already acted, pulling matter into denser regions and leaving behind quiet voids. The idea of the interplay of gravity is key to understanding this behavior. Gravity does not come from a single object. At every point in the universe, the gravitational environment reflects the combined mass of nearby and distant objects. Nearby objects have a strong influence, while distant objects have weaker influence. Together, they form a continuous gravitational background rather than isolated zones of influence. Therefore, gravity cannot be escaped simply by moving far away from objects. Distance alters the balance between these influences, but it does not eliminate them entirely. Even in the most empty regions of space, gravity still governs how matter moves and how structures evolve. Large-scale cosmic surveys have clearly revealed this structure. Observations from projects like the Sloan Digital Sky Survey and Dark Energy Survey have mapped the distribution of galaxies across enormous spaces. These maps show that galaxies are not scattered randomly. They form a vast cosmic web, often referred to as the cosmic web, consisting of threads, clusters, and large voids. This structure has formed over billions of years solely through gravitational interactions. The cosmic voids are sometimes mistaken as places without gravity. In reality, they are proof of gravity at work. These areas are empty because gravity has pulled matter out of them. Small differences in the density of matter in the early universe were amplified over time by gravity, drawing matter into denser regions. These voids continue to grow, expand, and regenerate under gravity's influence. From the perspective of general relativity, empty space has never truly been empty. Space-time exists everywhere in the universe, regardless of how much matter is present. The geometry of space-time reflects the total mass and energy of the universe, including contributions from distant objects outside the immediate environment. In areas with little nearby matter, space-time is nearly flat, but it is never entirely free from curvature. This explains why movement in deep space can still be predictable. Spacecraft moving between planets are not drifting aimlessly. Their paths are guided by the combined gravity of the Sun, planets, and even more distant objects. Even when a spacecraft appears to be moving through empty space, its orbit reflects a carefully calculated gravitational landscape created by multiple sources. Gravity in empty space also plays a crucial role in the long-term evolution of the universe. Over short periods, weak gravitational effects may seem insignificant. However, over billions of years, they accumulate. The small accelerations, though not easily noticed, gradually reshape the structure of the universe throughout its history. Galaxies slowly move closer to one another. Groups of galaxies form clusters. Clusters merge into larger systems. All of this doesn't require strong gravity from nearby objects. It simply arises from the continuous interplay of gravitational influences. Understanding gravity in empty space helps eliminate the idea that gravity must be tied to visible matter nearby. Gravity is not something that only appears near planets and disappears elsewhere. It is a continuous feature of the universe, woven into the very fabric of space-time. What changes from one place to another is not the presence of gravity, but the intensity and balance of its influence. Viewed this way, gravity explains why it can be sensed locally, even though it is a universal force. At every point in the universe, nearby objects dominate the perception of gravity. Distant objects contribute quietly, creating a background condition rather than distinct movement. Gravity is always present, but how it manifests depends on the scale of the objects. Empty space is not a place without gravity. It is a place where gravity becomes more subtle rather than stronger. Without nearby objects to mark its presence, its influence spreads gradually, forming motion and structure over vast distances. What may seem empty actually still has structure. What seems inactive is still governed. Gravity does not require dense areas to exist. It only needs matter somewhere in the universe to leave its mark everywhere. Gravity not only guides movement and forms structures, but also affects time itself. This idea may feel strange, because time is typically experienced as something stable and universal, passing at the same rate everywhere. In daily life, moments seem identical whether we're in the city, on a mountain, or underground. However, according to modern physics, time does not pass at a single universal rate. It changes according to gravity. This effect is called gravitational time dilation, a prediction of Albert Einstein's general theory of relativity. The core idea is that gravity and time are linked through the geometry of space-time. Where gravity is stronger, space-time curves more. This curvature affects not only how objects move, but also how time passes. In areas with stronger gravity, time passes more slowly. In areas with weaker gravity, time passes more quickly. This difference is not noticeable in most everyday situations, but it is real, measurable, and unavoidable. Two identical clocks placed at different gravitational intensities will not stay in sync. One clock will run slightly faster than the other. Near Earth's surface, gravity is stronger than at higher altitudes. A clock on the ground will run slightly slower than a clock on a satellite in orbit. The satellite, farther from Earth's mass, experiences weaker gravity, so the clock on the satellite runs faster. The difference is tiny, only a fraction of a second over a long period, but it accumulates. This is not just a theoretical curiosity. This effect has been measured directly. Experiments using atomic clocks, which can keep time with great precision, have proven gravitational time dilation, even when the altitude difference is small. A clock placed a few meters higher will run slightly faster. This effect is very subtle, but modern tools are sensitive enough to detect it. One of the most important practical proofs of gravitational time dilation comes from the Global Positioning System, GPS. Satellites orbit Earth at high altitudes and speeds. The atomic clocks on these satellites are affected by two time dilation effects. Because the satellites move fast, special relativity predicts that their clocks will run slower. However, because they are farther from Earth and experience weaker gravity, general relativity predicts that their clocks will run faster. Both of these effects must be taken into account. The gravitational effect is stronger than the motion effect, so the clocks on GPS satellites actually run faster compared to those on the ground. Engineers deliberately account for this difference. Without this adjustment, errors in GPS positioning would increase rapidly, leading to location errors of several kilometers in a single day. The system works accurately because gravitational time dilation is real and well understood. However, gravitational time dilation is still unnoticed in daily life. The main reason for this is scale. The difference in the strength of gravity between typical locations is very small, and the time difference accumulates very slowly. Over a human lifetime, the difference in time experienced at sea level and at the top of a mountain is measurable, but only a small difference. There is no noticeable sensation accompanying this change. There is no feeling of time slowing down or speeding up. The absence of this sensation does not mean that time behaves inconsistently. It means that human perception is not equipped to recognize such small differences. Just like gravity feels stable despite small changes, time also feels steady because these changes are too subtle to directly perceive. This effect becomes more pronounced near objects with extremely strong gravity. Near neutron stars or black holes, gravitational time dilation becomes extremely powerful. Time near the surface of a neutron star runs much slower than time farther away. Near the event horizon of a black hole, the time dilation is so strong that from the perspective of a distant observer, time appears to slow down almost completely. Although these extreme cases are not part of everyday experience, they follow the same principles as time near Earth. The difference is simply in the degree, not in the nature of the effect. Gravity affects time everywhere. Strong gravity makes this effect more apparent. Weak gravity makes it subtle. Gravitational time dilation also reinforces the idea that time is inseparable from space. Together, they form spacetime, a unified structure governed by mass and energy. Where spacetime curves more, both motion and time behave differently. This unity explains why gravity affects clocks without the need for any additional mechanism. Time is part of the structure that gravity forms. It is important to clarify that this does not mean time passes incorrectly or unpredictably. Time behaves exactly as described by the basic geometry of spacetime. Clocks do not malfunction in strong gravity. They run normally according to the local conditions of their environment. Only when comparing clocks in different gravitational environments does the difference become apparent. Each clock measures its own time, the time experienced in that local area. There is no universal clock in the universe that counts time at the foundation of the cosmos. Time is local, just as gravity is local. What feels simultaneous in one place may not entirely align with what feels simultaneous in another place when gravity differs. This challenges the intuitive ideas of time being absolute. In Newtonian physics, time is viewed as universal, passing at the same rate everywhere regardless of conditions. General relativity replaces the old concept of time and space, providing a more flexible image where time changes according to the shape of space-time. Gravity affects this shape, and time changes accordingly. However, this does not make time chaotic or subjective. The rules of gravitational time dilation are very precise and consistent, allowing for predictions with excellent accuracy. Gravitational time dilation changes according to gravity in a measurable, calculable, and adjustable way. The effect of gravity on time also has significant impacts on the long history of the universe. Over billions of years, regions of the universe with different gravitational environments accumulate differing experiences of time. Clocks near massive galaxy clusters run slightly slower than clocks in cosmic voids. While this difference is very small, it is real and has been woven into the timeline of the universe. Understanding gravitational time dilation expands the role of gravity beyond structure and motion. Gravity not only guides objects along their paths but also determines the speed at which events occur. It influences the passage of time, how signals propagate, and the development of history. The connection between gravity and time deepens the idea that gravity is not just a force among many others. It is a fundamental feature of space-time. Time is not separate from the structure of the universe. Gravity itself shapes and acts upon time. As gravity changes, time responds accordingly. As matter accumulates, the pace of time changes subtly. In daily life, this effect remains invisible. Clocks on the table run at the same pace. Time feels stable. But beneath this quiet surface, time gently responds to gravity, stretching and contracting in ways that only precise measurements can reveal. The awareness of this does not make time feel unstable. Instead, it places time in a larger context. Time is not separated from the structure of the universe. It is shaped by it. Gravity not only affects falling objects or planets orbiting stars, but it also influences the rhythm of moments within time itself. Gravity reaches its extreme levels in the universe around neutron stars and black holes. These objects represent environments with such concentrated mass that space-time is pushed to its limits. The basic principles that govern falling apples or satellites orbiting planets still apply, but their effects become so powerful that they surpass intuition and require careful explanation. A neutron star forms when a massive star runs out of nuclear fuel and collapses under its own gravity. During this collapse, the star's core is compressed to an extreme level, causing protons and electrons to combine into neutrons. The result is an object with more mass than the Sun but only a few tens of kilometers in radius. This concentration creates an extremely powerful gravitational field. Near the surface of a neutron star, gravity is billions of times stronger than Earth's gravity. An object dropped from a small height will collide with the surface of the neutron star at a speed close to the speed of light. The mountains, if they could be called mountains, are only a few centimeters high before they collapse under their own weight. Matter here behaves in an unfamiliar way because gravity governs every aspect of structure and motion. The escape velocity is a useful way to describe this level of strength. Escape velocity is the speed that an object must reach to escape a gravitational field without additional propulsion. On Earth, the escape velocity is around 11 kilometers per second. On a neutron star, the escape velocity is nearly a significant fraction of the speed of light. This means that once matter is near the surface, escaping becomes incredibly difficult. The enormous gravity of the neutron star also creates strong tidal forces. Tidal forces arise because gravity pulls more strongly on parts of an object closer to the star than on parts farther away. Near Earth, tidal forces are relatively mild, only affecting ocean waves. However, near a neutron star, these tidal forces are incredibly strong. Objects can be stretched, compressed, or even torn apart due to the differences in gravitational forces across their length. The curvature of space-time near a neutron star is extremely strong. Paths that would normally be straight elsewhere become sharply curved. Light is also affected, bending around the neutron star and altering how it appears to distant observers. Time dilation becomes evident. Clocks near the surface of a neutron star run much slower compared to clocks farther away. These effects are not theoretical curiosities but are accurately predicted by general relativity and have been observed in practice. Black holes are the result of even stronger gravitational collapse. When a star's core collapses and exceeds a certain mass, no force can stop the inward pull of gravity. The result is a region of space-time where nothing can escape once it crosses a critical boundary, known as the event horizon. The event horizon is not a physical surface but a boundary in space-time. Outside it, escape is still theoretically possible, but inside, all paths lead inward. The escape velocity at the event horizon is the speed of light. Since nothing can move faster than light, escaping becomes impossible. It is important to clarify that the gravity at the event horizon is not infinite. Objects crossing it do not encounter an abrupt wall or crushing force immediately, especially for large mass black holes. What changes is the structure of space-time itself. Directions that would normally point outward now point inward. Falling inward becomes inevitable, much like moving forward in time. The closer one gets to the center of a black hole, the more intense the curvature of space-time becomes. Tidal forces increase significantly. In some cases, these forces can stretch objects into thin shapes, a phenomenon known as spaghettification. This occurs because the gravitational force at the near side of an object is much stronger than at the far side. Escape velocity and spacetime curvature are closely related in these environments. As gravity increases, spacetime curvature becomes even stronger. Motion becomes increasingly restricted. The idea of gravity as a simple pulling force gradually becomes inaccurate. Instead, gravity becomes a geometry of spacetime. Objects follow paths that are naturally guided by the curvature of spacetime itself. For a long time, neutron stars and black holes were only studied indirectly. Their gravity revealed their presence through its effects on nearby matter, such as stars orbiting invisible companions, gas heating up and emitting radiation as it spirals inward, or precise changes in the pulses emitted by rapidly rotating neutron stars. In recent years, direct observational evidence has completely changed our understanding of them. Gravitational wave observations by the Laser Interferometer Gravitational Wave Observatory, LIGO, have detected gravitational waves caused by the merger of black holes and neutron stars. These waves are ripples in space-time created by accelerating massive objects in extremely strong gravitational fields. This discovery has confirmed important predictions of general relativity and opened a new perspective on gravity at extremely strong levels. Another breakthrough came from the Event Horizon Telescope, a global network of radio telescopes which produced the first images of a black hole's shadow. These images show light bending and being captured by the immense gravity near the event horizon. These images are not pictures of the black hole itself, but rather the gravitational effects it has on surrounding matter and radiation. These observations have firmly rooted extreme gravity in reality. Neutron stars and black holes are not bizarre theoretical phenomena. They are common outcomes of stellar evolution, present throughout galaxies, influencing the surrounding environment solely through gravity. Despite their immense intensity, these environments do not require new physical laws. The equations that describe gravity near Earth also describe gravity near a black hole. The difference is just in scale. When matter concentrates enough, familiar effects become powerful. Near extreme objects like neutron stars and black holes, gravity becomes dominant, overwhelming all other factors and revealing features of spacetime that are not visible in other regions of the universe. Despite its immense strength, gravity still behaves according to predictable rules. The paths of motion and time dilation can still be calculated and measured accurately. Gravity does not change its nature in these extreme environments. Instead, it reveals its true nature more clearly. Gravity, whether from small objects or extremely large ones like neutron stars and black holes, is the manifestation of the same phenomenon, only differing in scale. These extremes do not negate the stability of gravity in other environments. They simply make gravity more noticeable under special conditions. Stars within galaxies do not exist independently but orbit a common center. This center is not a specific object but the combined mass of billions of stars, gas, dust, and invisible objects scattered throughout the galaxy. Each star follows an orbit shaped by this collective gravitational field, creating vast arcs that may take hundreds of millions of years to complete. However, these stellar orbits are not straight lines or perfect. They are affected by the uneven distribution of matter in the galaxy. Areas with higher matter density will create stronger gravitational effects, causing stars to change their orbits over time. Stars gradually move inward or outward, tilting their orbital planes or slightly changing their speed, all influenced by gravity. In star clusters, gravity forms a system of companion stars, where stars are born from the same gas cloud. Initially, these stars are tightly compressed, and their gravity holds them together in a common system. Each star feels the pull from many neighboring stars simultaneously, creating a constantly changing pattern of influences. In open star clusters, where there are hundreds or thousands of stars, gravity is strong enough to keep the group together for millions of years. However, over time, interactions between the stars gradually change their motion. Stars that meet close to each other exchange energy. Some stars are pushed into wider orbits, others gain enough speed to escape the star cluster entirely. Gravity both holds and gradually dissolves these star systems. Globular clusters represent an even more extreme case. These ancient structures contain hundreds of thousands, sometimes millions of stars, compressed into relatively small spaces. Gravity dominates the entire internal dynamics. The movements of the stars are fast and complex. Interactions occur frequently. Nevertheless, these globular clusters can remain intact for billions of years, held together by the combined gravitational pull of all the stars within them. In these star clusters, gravity not only governs motion but also the long-term evolutionary process. Massive stars tend to move toward the center through a process called mass segregation. Lighter stars will drift outward. Over time, this star cluster develops a layered structure due to gravitational interactions. This process of stratification occurs slowly, imperceptible within a human lifetime, but very clear when viewed across the history of the universe. Gravity continues its work, whether within star clusters or across galactic disks. Stars do not move in straight lines through space. Stars within a galaxy do not move randomly. Instead, they follow curved orbits, shaped by the overall mass distribution of the galaxy. In spiral galaxies, gravity plays a central role in maintaining the structure of the arms and disk, causing stars near the center to orbit faster, while stars farther out move more slowly. Even though stars move at different speeds, the galaxy remains stable, not tearing apart. Gravity not only helps maintain the galaxy's structure, but also shapes how stars move and interact with one another. Stars that are close to each other can influence each other, changing their orbits or even ejecting planets from their systems. In sparse regions, stars move through space without major disruptions, but in denser areas, gravity can cause significant disturbances and changes in the star's movements. The motion of stars is not a random change, but a continuous process governed by gravity. Stars move from their birthplace, star clusters disperse, and new groups form over time. Gravity alters and reshapes the star regions in galaxies, creating predictable patterns of movement. Though the motion of stars may seem slow and unnoticed in the short term, on a cosmic scale, the gravity from stars and star clusters continues to shape large-scale patterns. Stars and star clusters move through space, influencing each other and creating long-lasting star systems. Gravity in these environments not only holds stars together but also drives the change and evolution of the universe over billions of years. Astronomers have studied and observed the differences between visible mass and gravitational effects, leading to the discovery of dark matter. Although dark matter cannot be seen directly, gravity reveals its presence through its influence on the movement and interaction of stars. This expands our understanding of gravity and what it can reveal about the universe. The motion of galaxies is a clear example of how gravity governs everything in the universe. Galaxies do not remain still but are always moving and evolving over time, driven by gravity. Although this change happens slowly and is not immediately noticeable, gravity sustains the motion of stars and galaxies over billions of years. Gravity not only affects stars but also shapes the evolution of star systems and clusters. In globular clusters, heavier stars gradually move toward the center, while lighter stars drift outward. This structure develops slowly, not easily noticed over short periods, but it becomes very clear when viewed from the perspective of cosmic history. With the powerful influence of gravity, stars and galaxies move, evolve, and change, creating a universe in constant motion. Gravity not only holds everything together but also drives the change and evolution of the universe over time. The spiral arms in galaxies are not fixed structures made from the same group of stars forever. Instead, they are regions where stars, gas, and dust temporarily concentrate together. Gravity causes matter to gather as it moves through the galaxy's disk, much like traffic slowing down on busy roads. When gas clouds are compressed, the star formation process is triggered, brightening the spiral arms and making them more visible from afar. This process depends on gravity acting on the entire galaxy. The combined mass of stars, gas, and other matter creates a gravitational field that keeps the galaxy's disk stable and allows the spiral patterns to persist. Without enough gravitational force, the galaxy's disk would disperse over time. When astronomers began measuring the motion of stars in galaxies, they discovered a surprising result. According to classical theory, stars far from the galactic center should rotate more slowly, just as planets farther from the Sun move more slowly. However, observations showed that stars farther out move faster than expected, and their speeds hardly change regardless of their distance from the center. This led to a flat rotation curve and suggested that there was much more gravitational force than visible matter, hinting at the presence of dark matter. Dark matter does not emit, absorb, or reflect light, but its presence is completely inferred through gravity. Galaxies appear to be surrounded by huge dark matter halos extending beyond the observable edge. These dark matter halos provide the additional gravitational force needed to explain the flat rotation curves of galaxies. Thanks to gravity, stars rotate around a common center within galaxies. The gravity from dark matter helps stars in the outer regions move as quickly as they do because they must respond to the gravitational forces from both visible and dark matter. Without dark matter, many galaxies would not maintain their stability over cosmic time. Gravity explains why galaxies have different shapes. Spiral galaxies maintain their flat disk structures thanks to the balance between gravity and the angular momentum of the stars. Elliptical galaxies, on the other hand, have more random stellar motion, usually a result of galaxy mergers, causing energy to be redistributed through gravity. Galaxies are not static systems but are always evolving. Interactions between galaxies can stretch stars into tidal tails, distort spiral arms, and even trigger new star formation episodes. Over time, galaxies may merge, forming larger galaxies with new structures. This process takes hundreds of millions to billions of years. Gravity operates slowly but persistently, changing the shape of galaxies without haste. The current shape of a galaxy reflects a long history of gravitational influence rather than a static structure. Gravity not only affects stars in a galaxy but also influences gas clouds. As these gas clouds move into regions with higher density, they begin to form new stars, and in some cases, foster supermassive black holes at the centers of galaxies. Gravity acts as an organizer, directing matter to areas where this transformation occurs. The supermassive black hole at the center of a galaxy does not entirely dominate the galaxy's gravity. Instead, the motion of stars in the galaxy is primarily governed by the combined mass of the stars and dark matter, not just the central black hole. This highlights how gravity works collectively, not just limited to areas near the black hole but impacting the entire galaxy. Galactic dynamics research is increasingly refining our understanding of how gravity affects stars within a galaxy. Large-scale observational surveys and detailed simulations allow astronomers to compare predicted motion with actual data. When discrepancies occur, they do not point to the failure of gravity, but rather the absence of certain components in the galaxy's mass, which helps to further clarify gravity's role. Dark matter, although not observable directly, reveals its presence through gravity. Gravity requires the presence of dark matter to explain what is happening in galaxies. Dark matter does not emit, reflect, or absorb light, but its existence is inferred through gravity, and the dark matter halos surrounding galaxies extend beyond their observable edges. The movement of stars and galaxies through space provides clear evidence of gravity's influence, not just on visible matter but also on invisible matter. Over long periods, gravity not only governs matter, but also serves as a tool for astronomers to explore the hidden structure of the universe. Gravity is not just a force that binds objects together, it is also a diagnostic tool that helps uncover the vast structures within the universe. The movements of galaxies are not just random changes, but a process slowly driven by gravity over millions to billions of years. Galaxy clusters are the largest gravitationally bound structures in the universe. The galaxies within a cluster do not remain stationary but move through the cluster's gravity, orbiting a common center of mass, formed by all the matter present, including both visible and dark matter. These movements are slow but persistent. A single orbit within a galaxy cluster can take billions of years to complete. Gravity holds the galaxies together, and even when galaxies pass through each other without colliding, they maintain their cohesion within the galaxy cluster. Gravity not only keeps objects together but also helps them maintain their structure over the vast timescales of the universe. The stability of galaxy clusters depends not only on visible matter, but also on dark matter, which explains why galaxy clusters can exist for billions of years without dispersing. Gravity binds them together, and even with changes in the motion of individual stars, the overall cohesion remains strong. Gravity in galaxy clusters primarily comes from dark matter, a type of matter that cannot be seen but has a strong influence on the movement of matter within galaxies. These dark matter halos are spread throughout galaxy clusters, and the gravity they create can be observed through gravitational lensing. When light from a distant galaxy passes through a large galaxy cluster, the light's path is bent, creating distorted images, elongated arcs, or even duplicates of the same background galaxy. Thanks to gravitational lensing, astronomers can determine the mass distribution within galaxy clusters. Through these observations, they discovered that there is more mass than can be seen, which proves the existence of dark matter. Space telescopes like Hubble and James Webb, as well as X-ray observatories like XMM Newton and Chandra, have played an important role in observing and detecting dark matter through lensing images and X-rays emitted from hot gas clusters. Gravity not only holds galaxy clusters together, but also governs their evolution. As galaxies fall into a cluster, they move faster and can be distorted by strong tidal forces. The gas clouds in these galaxies can be torn apart as they pass through the hot intercluster medium. Although these processes occur slowly, they are highly dynamic, changing galaxies over time. Galaxy clusters are not isolated systems but are connected through strands of dark matter and galaxies, forming a vast cosmic web that extends over hundreds of millions of light years. Gravity plays a role in connecting and growing these clusters, driving the formation and development of large structures in the universe. Gravity not only affects galaxies but also the dark matter network, binding them together. The distribution of dark matter in the universe has formed over time, stemming from small density differences following the Big Bang. Gravity has transformed these small differences into massive, slow-moving networks, creating the order and structures we see in the universe today. As galaxy clusters move through space, gravity not only keeps them together, but also helps them maintain stability and evolve over billions of years. Observations of gravitational lensing and the movement of stars within clusters help test and confirm current gravitational theories, especially general relativity. For example, in the Bullet cluster, when galaxy clusters collide, the separation between visible matter and dark matter becomes clear, supporting the hypothesis of dark matter's existence and demonstrating that gravity is the key factor in maintaining the structure of galaxy clusters. Gravity between galaxies not only links matter together but also helps them grow and change, creating enormous and enduring structures in the universe. Gravity not only holds individual galaxies together but also connects them into a larger system, forming a vast cosmic network. Gravity acts as an organizer, linking objects and creating the giant cosmic structure we see today. However, gravity is not the only factor governing the universe. The universe is expanding, and the expansion of space-time increases the distance between galaxies over time. Although the expansion of space causes galaxies to gradually move farther apart, gravity continues to act strongly to hold galaxies, star systems, and star clusters together. This expansion is not the movement of galaxies through space, but rather the uniform stretching of space-time. This is called the expansion of the universe, and it continues, increasing the distance between galaxies. Still, gravity governs star systems and galaxies, preventing them from expanding. Gravity holds galaxies together, but on a larger scale, the expansion of the universe is stronger than gravity, causing galaxies to move farther apart. The interaction between expansion and gravity shows that gravity is not always dominant. At larger scales, the expansion of the universe can overcome the gravitational pull, causing galaxies to drift apart over time. The expansion of the universe was first recognized through observations showing galaxies moving away from each other, and the farther galaxies are, the faster they move. This relationship, known as Hubble expansion, reflects a uniform expansion of space, rather than the movement of galaxies through space. While the expansion of the universe becomes more evident, gravity still plays a crucial role in keeping galaxies and star clusters together. They are not expanding internally because gravity is strong enough to keep them intact, preventing them from dispersing. However, the expansion becomes apparent only at larger scales, where galaxies are pulled farther apart, and the space between them expands. One of the important discoveries related to the expansion of the universe is that the universe is not just expanding, but it is accelerating. This can be explained by a new factor called dark energy. Dark energy not only accelerates the expansion of spacetime but also has the opposite effect on gravity. It does not pull matter together but directly influences the expansion of the universe. Dark energy is evenly distributed throughout space and cannot be seen directly. Its existence is inferred from observations of supernovae and cosmic microwave background (CMB) radiation, showing that the universe is expanding faster than what could be explained by just dark matter. These observations have strengthened the hypothesis of dark energy's existence, marking a breakthrough in our understanding of the universe's evolution. Through these observations, gravity and dark energy work together to control the evolution of the universe, although they have opposing effects. Gravity connects galaxies and star systems, while dark energy pushes them apart. The interaction between these two factors not only creates the expansion of the universe, but also helps us understand the structure and development of the universe over time. Data from the Planck telescope indicates that the universe is primarily made up of dark energy, with dark matter and ordinary matter contributing a smaller portion. The balance between dark energy and gravity is a key factor in how expansion and gravity interact throughout the history of the universe. In the early stages of the universe, gravity dominated, pulling matter together. However, as the universe expanded and the matter density decreased, dark energy began to have a greater influence, accelerating the expansion at an increasingly rapid rate. Although the expansion is accelerating, gravity never ceases to act. It still plays an important role in the formation of galaxies and galaxy clusters, pulling them together along dark matter filaments. Gravity not only holds cosmic systems together but also maintains their structure even as space expands. It is important to clarify that the expansion of the universe does not separate systems with strong gravity. Expansion only affects the space between unbound systems, while gravity still governs the connection of galaxies and stars. Expansion and gravity do not conflict but are two different manifestations of a unified space-time structure, where expansion describes the global growth of space and gravity bends space around massive objects. The balance between expansion and gravity explains why the expansion does not disrupt the formation of structure in the universe too quickly. Gravity continues to govern the formation of galaxies and galaxy clusters. Even though expansion causes galaxies to drift farther apart, galaxies remain stable and continue to interact in clusters, forming robust structures over time. The universe's expansion is currently increasing, but gravity remains indispensable. While expansion may separate these systems over time, it cannot erase the effects of gravity within these structures. Gravity is not only a force that binds objects in the universe, but also an important tool in forming and maintaining the large-scale structure of the universe. As we look toward the future of the universe, expansion will continue, and galaxy systems will continue to separate. But gravity will play a crucial role in maintaining the stability of galaxies and star clusters. Gravity will always be the determining factor in the formation and evolution of cosmic structures. Entering an endless vast space, we realize that the operation of gravity is the key factor that gives the universe structure, existence, and development in a constantly changing landscape. Gravity is the force that pulls matter together, maintaining the long-term life of systems and organizing the universe amidst constant expansion. When we combine gravity with the expansion of the universe, the overall picture becomes clearer. The universe is not simply separating, nor is it contracting. It is simultaneously doing both, depending on the perspective. Expansion provides the foundation, while gravity writes the details. In this relationship, gravity is not overwhelmed by expansion, but is contained within it. Together, they describe a universe that is constantly evolving, stretching, and organizing itself based on deep and consistent principles. Gravity is the thread connecting the universe's history, from the dense initial moments to the present structured state and further into the future, where space continually expands. However, gravity continues to shape what remains within reach. At the larger scales, gravity reveals a universe that is neither random nor evenly distributed. Matter is arranged in a sophisticated pattern of filaments, star clusters, and vast voids, all forming a large structure called the large-scale structure of the universe. This structure spans hundreds of millions of light-years and is the result of gravity's patient action since the universe's earliest moments. These great patterns are often referred to as the cosmic web. Galaxies are not randomly scattered through space. Instead, they lie along long filaments, intersecting at dense nodes. Between these filaments are vast expanses of space where very few galaxies exist. This layout is not random. It is the natural result of gravity, amplifying the small initial differences that existed in the early universe. Shortly after the Big Bang, matter was distributed nearly evenly but imperfectly. Small fluctuations in density existed at the level of only a few parts per 100,000. These slight variations were enough to cause large changes. Over time, gravity pulled more matter into regions that were denser than average. As matter accumulated, gravity became stronger, pulling more matter in. Regions that began to thin out lost matter from surrounding areas and became even emptier. This process unfolded over billions of years. Gravity does not act hastily or violently. It works steadily, transforming subtle irregularities into massive structures. The filaments grew longer and thicker. Star clusters formed where filaments intersected. The voids expanded as matter receded. The universe slowly developed into a clear architecture, almost entirely shaped by gravity. The filaments of the cosmic web themselves are enormous. They can stretch hundreds of millions of light-years and contain countless galaxies along their length. These filaments act as gravitational roads, guiding matter to denser regions. Gas flows along them. Galaxies slowly move toward the nodes, where star clusters exist. Gravity creates direction without urgency. At the intersections of the filaments, gravity is strongest. These areas contain galaxy clusters, the most gravitationally bound structures in the universe. Their development is continuously nurtured by matter flowing into them along the filaments. Over time, large star clusters grow, pulling in galaxies and gas from surrounding regions. The large-scale structure is not a random result. It directly stems from how gravity operates in an expanding universe filled with matter and dark matter. Particularly, dark matter plays an important role because it does not interact with light or radiation. Dark matter began to concentrate earlier than ordinary matter. Its gravitational force created the initial structures on which the visible structures later formed. As ordinary matter cooled and slowed down, it fell into the gravitational wells created by dark matter. Gas accumulated, stars formed, galaxies appeared. The visible universe we see today is imprinted on the invisible structural framework created by gravity's influence on dark matter. What we see through telescopes is only the bright edge of a much larger structure. This is demonstrated through detailed simulations of cosmic structure formation. Using supercomputers, scientists simulate the development of the universe from the initial density fluctuations to the present day. These simulations combine known physical laws, including gravity, cosmic expansion, and the properties of dark matter. As they progress in time, they create cosmic webs, similar to what we observe in the universe. Projects like the Millennium Simulation and later large-scale cosmological models show how gravity alone, with the right initial conditions, can create the cosmic web. The agreement between the simulations and observations is impressive. The filaments, star clusters, and voids appear naturally without the need for additional organizing forces. These simulations also reveal the timescales involved. Large-scale cosmic structures form slowly. Each galaxy evolves over billions of years. The filaments persist even longer. Gravity operates over immense timescales, shaping the universe gradually rather than suddenly. Nothing happens quickly at this scale. What is particularly remarkable is that gravity creates order without a design. There is no blueprint directing matter into the filaments. The structure emerges because gravity continuously and consistently amplifies small differences. The result is a universe that is structured but not rigid, with patterns but not symmetrical. Even at larger scales, gravity does not act alone. The expansion of the universe continues behind the scenes, stretching space while gravity pulls matter together in smaller regions. The balance between these two effects determines how structures develop and when they cease to evolve. In the distant future, accelerated expansion may slow the formation of new large-scale structures, but the structures already in place will persist. Large-scale gravity also affects how information moves. Light from distant galaxies follows paths bent by the gravitational landscape it traverses. The filaments and star clusters curve space-time, subtly altering the paths of photons. This gravitational lensing effect provides another way to map the cosmic structure and confirm the presence of mass where little light is observed. From this perspective, gravity becomes an architect rather than just a force. It does not deliberately design shapes, but it creates an organized universe. It links the small fluctuations from the earliest moments of the universe to the grand patterns we can see today. Gravity connects the origins of the universe to its present shape through continuous influence. The scale involved is difficult to grasp. The distance between large structures is measured in hundreds of millions of light-years. The timescale spans most of the universe's history. Gravity operates very slowly and over vast distances, making its effects invisible within a human lifespan. However, this is undeniable when viewed from the entire lifespan of the universe. This perspective completes the expansion of scale. Gravity begins as a familiar force beneath our feet. It becomes the guide for movement, the sculptor of stars, the connector of galaxies, and ultimately the organizer of the universe. Each step, the same principles apply, only the scale changes. When observing gravity at larger scales, we will also reconsider emptiness. Voids are not the failure of structure, they are part of that structure. They exist because gravity has moved matter elsewhere. Even absence bears the imprint of gravitational influence. The large-scale structure of the universe is a record of gravity's long, patient action. Nothing happens in haste. Nothing happens suddenly. Over billions of years, gravity has gently transformed irregularities into great order. It does so silently, persistently, and without pause. In this sense, gravity is not just a force acting in the universe. It is the force that has shaped the very form of the universe itself. The cosmic web is gravity made visible, written across space. At larger scales, gravity shows what it always does. It takes what already exists, amplifies the differences, and allows natural structures to form. From near-perfect uniformity to intricate architecture, gravity remains the guiding force, patiently shaping the universe into the form we observe today. But at the smallest scales, gravity becomes strangely silent. The familiar descriptions that work so well for planets, stars, and galaxies start to become ambiguous. This is not because gravity disappears, but because the tools used to describe it are no longer adequate for the principles of modern physics. At these scales, gravity encounters quantum mechanics, and these two theories have yet to speak the same language. Quantum mechanics is the theoretical framework that describes how nature operates at very small scales. It governs atoms, particles, and the forces between them. Its predictions are extraordinarily accurate. Technologies like semiconductors, lasers, and atomic clocks rely on quantum mechanics every day. Meanwhile, gravity is just as accurately described by general relativity, but only at larger scales. Each theory works brilliantly within its domain. The difficulty arises when both are needed simultaneously. In extreme situations, such as the early moments of the universe or inside black holes, both gravity and quantum effects may play a significant role. General relativity views space-time as smooth and continuous. Quantum mechanics, on the other hand, sees reality as discrete and probabilistic. When applied together, mathematical conflicts arise, and the theories cannot be reconciled. This unresolved tension has driven physicists to search for a theory of quantum gravity, a theoretical framework that describes gravity in quantum terms. Currently, no complete and experimentally verified theory exists. Instead, there are several competing ideas, each attempting to bridge this gap in different ways. One approach is called loop quantum gravity. This theoretical framework suggests that space-time itself has a particle-like structure at extremely small scales. Instead of being smooth, space might be made up of tiny loops or networks that interweave. In this view, gravity emerges from how these fundamental units connect and evolve. Time and space become quantized, just like the energy levels in an atom. Another major approach is string theory. In string theory, the fundamental components of nature are not point particles, but tiny vibrating strings. Different vibration patterns correspond to different particles. Gravity naturally appears in this theoretical framework as a special vibration mode associated with a particle called the graviton. String theory requires additional spatial dimensions beyond the familiar three, which are compacted and hidden from direct observation. Both approaches have sophisticated and internally consistent mathematics. However, neither approach has been confirmed through experimentation. The scales at which quantum gravitational effects would become apparent lie beyond the reach of current experiments. The energy required to directly probe these effects is far beyond the capabilities of any existing technology. This is partly why gravity at small scales remains so elusive. Gravity is incredibly weak compared to other fundamental interactions. At the level of particles, its effects are overwhelmed by electromagnetic and nuclear forces. Therefore, directly detecting the quantum behavior of gravity is an immense challenge. Nevertheless, gravity cannot be ignored at small scales. Questions about the origin of space-time, the nature of singularities, and the moments following the Big Bang all require an understanding of gravity under quantum conditions. Without such a theory, these questions will remain only partially answered. Clarifying what is known and what is not known is crucial. Currently, there is no experimental evidence confirming how gravity works at the smallest scales. There is also no consensus on whether space-time is continuous or discrete at this level. No particle has been confirmed to carry gravitational interaction in the same way photons carry electromagnetic interactions. What is known is that current theories are incomplete in this domain. General relativity predicts the appearance of singularities, where curvature becomes infinite, such as at the center of black holes. Quantum mechanics suggests that such infinities are signs of a breakdown in the theory rather than a physical reality. Reconciling these two viewpoints remains one of the biggest challenges in theoretical physics. Researchers continue to look for indirect ways to test ideas about quantum gravity. Observing black holes, gravitational waves, and cosmic microwave background radiation may provide clues. Subtle patterns in these phenomena could hint at underlying quantum structures. However, to date, no conclusive evidence has emerged, but the search continues. This uncertainty stands in stark contrast to gravity at larger scales. At larger scales, gravity is well understood, measured, and confirmed with extraordinary precision. Predictions from general relativity match observations of galaxies and galaxy clusters. The theory works perfectly where the curvature of space-time is gentle and quantum effects can be neglected. However, at small scales, certainty gradually fades. Gravity becomes a question rather than an answer. This does not represent failure, but honesty. Physics advances through awareness of the limits of our understanding. Gravity at the smallest scales marks one of these limits. The absence of a complete theory does not diminish the role of gravity. On the contrary, it highlights the fundamental nature of gravity. Gravity resists simplification. It connects geometry, motion, time, and structure in ways that we only partially understand. There is also a silent symmetry in this uncertainty. Gravity was the first force to be described mathematically, and it remains the last to be fully integrated into the quantum picture. The force that shapes the largest structures in the universe is also the force that defines the limits of current knowledge at the smallest scales. Currently, gravity at the smallest scales remains an open question. Many ideas exist. None have been confirmed. What is clear is that gaining a deeper understanding of gravity will require new concepts, new mathematics, and new methods to test nature. This uncertainty does not weaken what is known in other realms. Gravity operates predictably through planets, stars, galaxies, and the entire universe. The mystery only lies at the extremes where existing theories overlap. By acknowledging this limit, gravity takes on another characteristic. It is not just a force or a geometric effect, but a guide to what remains unknown. Gravity marks the boundary between confident description and ongoing exploration. At the smallest scales, gravity reminds us that our understanding is still incomplete. The universe still holds layers of structure beyond current accessibility. What has been learned so far works very well. What remains unresolved points to discoveries in the future. In this way, gravity at the smallest scales does not close the story. It leaves the story open, silently indicating that even the most familiar features of the universe still have depths yet to be fully understood. Gravity feels stable because the human body has developed within a very narrow range of gravitational force and has never known anything else. From the earliest moments of development, gravity has been present as an unchanging foundational condition. Muscles form against it. Bones develop under its influence. Balance systems self-regulate in response to it. By the time consciousness develops, gravity has become so deeply embedded that it is no longer recognized as a separate influence. On Earth, gravity is surprisingly stable within the span of a human lifetime. The mass of the planet doesn't change meaningfully from day to day. Its radius remains constant. The Earth's movement causes small changes, but these fluctuations are very subtle and predictable. As a result, the gravitational environment changes very slowly and very gently, to the point where it seems like a constant factor. What we perceive as a universal constant is actually a local condition, so stable that we fail to recognize its existence. The human sensory system is designed to detect changes rather than stability. Sudden changes in acceleration are immediately noticed. A stumble, a fall, or a jump will trigger reflexes and attention. Gravity's downward pull doesn't behave this way. Gravity is always present, always the same in our daily experience, and therefore, it becomes invisible to our perception. The brain treats it as a baseline rather than a signal. Evolution has reinforced this effect. Over millions of years, organisms on Earth have adapted specifically to the planet's gravity. Our bodies reflect this adaptation. Limbs are balanced to support weight efficiently. The circulatory system is designed to pump blood against gravity. Bone structure resists compression due to continuous loading. Even cellular processes respond to mechanical stress caused by gravity. Since each generation has experienced nearly identical gravitational conditions, there is no selective pressure to detect subtle changes. Recognizing a small change in gravity wouldn't provide a survival advantage when such changes are smaller than other fluctuations in the environment. Therefore, the perception system has evolved to disregard the small details of gravity and only respond to significant changes. This explains why minor changes in gravity on Earth go unnoticed. Gravity is slightly weaker at the equator than at the poles. It is also slightly weaker at higher altitudes compared to sea level. These differences are real and measurable, but they are much smaller than the threshold at which we can perceive them. The body automatically adjusts without conscious awareness. The vestibular system in the inner ear plays an important role here. This system senses acceleration and orientation, helping maintain balance. It doesn't measure gravity directly. Instead, it detects changes in movement relative to gravity. When standing still, the system doesn't receive any new information. Gravity is present, but it doesn't provide any change signal for the system to register. The same applies to muscles and joints. They respond to forces and loads. But once these forces stabilize, the feedback stabilizes as well. The sensation of weight becomes a default condition rather than a stimulus. Only when weight changes suddenly, such as when lifting something heavy or in free fall, does gravity become noticeable. This creates the impression that gravity is absolute and unchanging. In reality, gravity is only stable within the narrow range of human experience. Outside this range, gravity changes drastically. On the Moon, astronauts immediately notice the weaker gravity because it lies outside the familiar range of Earth. On Earth, the difference is too small to trigger the same reaction. Expectations of perception also play a significant role. The brain builds predictive models of the world. Objects are expected to fall. Movement is expected to require effort. Balance is expected to work in familiar ways. When these expectations are met, attention is minimal. When they are violated, perception increases. Gravity on Earth rarely violates expectations. It is this consistency that fosters trust. Gravity becomes something we can rely on without thinking. Chairs support weight. The floor is always beneath our feet. Objects behave predictably. This trust allows attention to shift to social relationships, problem solving, and environmental awareness. The result is a paradox. Gravity is one of the most influential forces in daily life. However, it is rarely considered. Gravity creates posture, movement, and affects health, but it always remains at a conceptual distance. It is always present but almost never noticed. Modern technology sometimes reveals the subtlety of gravity. Precision instruments can measure changes caused by underground structures, tidal forces, or celestial bodies passing by. Atomic clocks show time dilation due to gravity through small changes in altitude. These measurements show that gravity is not completely uniform, even locally. The body simply does not register these variations. Prolonged exposure to changing gravity highlights the deep adaptation of the body. Astronauts returning from extended missions often experience muscle loss, reduced bone density, and balance disorders. These effects occur because the body has adapted to a different gravitational environment and must then readapt upon return. What once felt stable is actually a specific condition the body depends on. This emphasizes an important point. Gravity feels stable not because it is universal, but because it is familiar. It is the condition in which perception has developed. Change makes it stand out. Stability hides it. When returning to Earth after experiencing gravity at different scales, this experience becomes complete. After considering gravity in stars, around black holes, through galaxies, and across the expanding universe, the daily downward pull now takes on new context. Now, it is not the default gravity of the universe. It is Earth's gravity. This does not make it any less real or important. It just becomes more specific. It belongs to this planet, with this mass, at this distance from its core. Life has adapted to it because it is present, not because it is inevitable. Understanding why gravity feels stable helps reconcile the familiar and the vast. The gentle stability underfoot is an expression of a larger phenomenon, one that behaves very differently elsewhere. What feels fixed is actually local. What feels universal is, in fact, contextual. Gravity feels stable because it has been stable here. The universe does not guarantee that stability everywhere. Earth simply provides a stable gravitational environment within a narrow range that perception has learned to treat as normal. Recognizing this does not disrupt daily life. Objects will still fall. Balance will still function, but it changes the experience. The sensation of downward pull is no longer just a foundation. It becomes a reminder that even the most familiar aspects of reality are formed by specific conditions. Gravity feels stable because it has silently shaped bodies and minds throughout their existence. Its stability is not a theorem of perception, but a consequence of prolonged exposure. What feels natural is not universal. It is local, learned, and deeply embedded in the body. When returning to human experience, gravity becomes both ordinary and noteworthy. It is the same interaction that curves spacetime and binds galaxies. Here, it manifests as a gentle, reliable pull, familiar not because it is simple but because it is always present. Gravity appears to be a universal feature of the universe, and fundamentally, it is. The same fundamental interaction governs falling objects on Earth, the motion of planets, the structure of galaxies, and the evolution of the universe itself. However, how gravity is experienced, measured, and manifested strongly depends on where it is encountered. Gravity is universal in principle, but local in practice. Across all the scales studied so far, gravity follows consistent rules. Mass and energy curve spacetime. Curved spacetime then guides motion. This theoretical framework applies everywhere, from the surface of a small moon to the edge of a galaxy cluster. What changes is not the theorem but the context. The amount of mass involved, how it is distributed, and the distance between objects all influence how gravity manifests. On Earth, gravity feels stable and familiar because the local conditions are stable. The mass, radius, and internal structure of Earth create a gravitational field that changes very little on the planet's surface. Human perception has developed within this narrow range, reinforcing the sense that gravity is fixed and uniform. In reality, even here, gravity changes subtly with altitude, latitude, and the geological structure below. These changes are real, but small enough to go unnoticed without precise instruments. As we move farther away, the variations become more noticeable. On the Moon, gravity is significantly weaker. On Mars, it changes again. Around the giant gas planets, it increases. These differences do not signify different types of gravity. They reflect the same interaction responding to different masses and sizes. The rules remain the same. The outcomes vary depending on the context. Inside stars, gravity does not just operate on a surface but throughout a volume of hot plasma. There, it balances nuclear fusion, adjusting stability and lifespan. In small celestial bodies like asteroids, gravity weakens to the point where structures become loose and fragile. Matter can hardly hold together. These environments feel completely different. However, they stem from the same principles applied at different scales. As the distance increases, gravity is no longer expressed through weight or falling objects, but through movement over time. Orbits become the primary manifestation. Stars orbit around the center of galaxies. Galaxies drift within clusters. Matter flows along strands stretching hundreds of millions of light years. Gravity guides these movements patiently, often requiring millions or billions of years for its effects to become apparent. At the largest scales, gravity acts as an architect. It amplifies small fluctuations left over from the early universe, shaping matter into a cosmic web. The cosmic strands, star clusters, and voids do not appear because gravity changes nature, but because it is allowed to act over vast distances and long periods. Structures form gradually without design, through continuous influence. At the smallest scales, certainty fades. Gravity resists easy integration with quantum mechanics. While general relativity describes gravity with extraordinary accuracy at large scales, it has yet to fully reconcile with quantum theory. This does not mean a contradiction. It marks the boundary of our current understanding. The same interaction governing galaxies also defines where knowledge becomes incomplete. Looking at the bigger picture, these differences might make us think there are many versions of gravity. In fact, they reveal a single interaction that continuously responds to the context. Gravity does not change mode. It does not become something else near black holes or fade in empty space. It manifests through mass, distance, density, and scale. This continuity is crucial. It means that extreme environments do not invalidate the rationality of familiar ones. Gravity near neutron stars does not contradict gravity felt on Earth. It extends it. The gentle pull underfoot and the intense curvature near black holes are both tied together by the same theoretical framework. One feels normal because it is local. The other feels extreme because it is distant in scale, not principle. Understanding gravity as a local experience helps reconcile the familiar with the strange. Gravity on Earth is not the standard by which all gravity should be measured. It is just one result among many. It feels central only because it is experienced continuously in a universe full of diverse gravitational environments. There is no single position that defines how gravity will feel. This perspective also clarifies why gravity can be both simple and profound. At the human scale, gravity can be easily summarized. Objects fall. Weight exists. Movement requires effort. At the cosmic scale, gravity bends space-time, curves light, slows time, and reveals invisible matter. The simplicity of local experience does not capture the depth of the interaction, but it does not distort it either. The consistency of gravity lies in its rules, not its results. The rules apply everywhere. The results differ because the universe is not homogeneous. Mass is distributed unevenly. Distances change. Structures form and dissolve. Gravity responds faithfully to what exists. This perspective avoids contradictions by accepting the context. Gravity is not gentle in some places and violent in others because it changes its nature. Gravity is gentle when mass is distributed widely and distances are large. It is strong when mass is concentrated. It is subtle when changes occur gradually. It becomes powerful when the curvature of space-time becomes extreme. The same principle explains why gravity can be almost unnoticed in everyday life but governs the evolution of the universe. Local stability hides transformation. The large scale reveals this. No perspective is wrong. Each perspective reflects a different slice of the same reality. Tracking gravity across environments, a coherent picture emerges. Gravity binds matter without rigidity. It guides motion without purpose. It shapes structures without design. It does so continuously, from the smallest scales that can be accessed to the largest scales that can be observed. This continuity also gives gravity a gentle reliability. Even when understanding is not complete, gravity still behaves consistently with what is known. The uncertainty does not lie in unusual changes in gravity, but in the limits of the current theory. What is understood fits smoothly across scales. Returning to the idea of gravity as a local experience, we focus on the perspective. Each observer experiences gravity from a specific place. That experience reflects local conditions rather than universal standards. Gravity on Earth feels normal because it is the condition in which perception has developed. In other places, gravity will feel different, but no less reasonable. This perception does not diminish the daily experience of gravity. It enriches it. The feeling of being pulled downward becomes an expression of a larger phenomenon, operating everywhere, shaping the universe in subtle and grand ways. Gravity does not contradict itself when scales change. It reveals more of itself. Each environment adds context rather than contradiction. From the gentle pull underfoot to the slow movement of galaxies, gravity remains the same, continuous interaction expressed differently. Viewed this way, gravity is not a singular feeling or a single equation. It is a relationship between mass, space, time, and motion, naturally adapting to the circumstances. Local experiences fit within a universal framework. What is familiar can comfortably stand next to what is vast. This understanding prepares for reflection rather than resolution. Gravity does not require a final summary. It invites perspective. It connects the immediate and the universal without forcing them to feel the same. In a universe full of change, gravity provides continuity. It operates everywhere but always at the local scale. It feels stable when conditions are stable. It feels strange when conditions are extreme. No experience fully defines gravity. Gravity is universal in its reach, local in its manifestation, and continuous across every scale explored so far. What changes is not gravity itself, but the place it is encountered and the degree to which it is perceived. This understanding provides a gentle stop for the journey. Gravity has been tracked from the ground beneath our feet to the structure of the universe and back, not as a collection of contradictions, but as a single interaction expressed differently across a diverse universe. What remains is not confusion, but coherence. Gravity operates everywhere. It simply does not operate the same way everywhere. Gravity is often thought of as something known. It is taught early, experienced continuously, and trusted without thought. Objects fall. Weight exists. Movement requires effort. These facts feel resolved, almost complete. And in many important ways, they are. Gravity is one of the most well-tested and reliable features of the physical universe. At the scales we are familiar with in daily life, gravity behaves predictably. It keeps objects tethered to the ground, holds the oceans in place, and controls the moon's motion around Earth. Classical descriptions explain these behaviors with astonishing accuracy. Modern physics deepens this picture, showing gravity as the curvature of spacetime created by mass and energy. Together, these descriptions allow for accurate predictions across a wide range of conditions at larger scales. The understanding remains robust. Gravity explains how planets orbit stars, how stars move within galaxies, and how galaxies cluster into groups and filaments. Observations confirm these models time and time again. Measurements of stellar motion, gravitational lensing, and the structure of the universe all align with the same fundamental theoretical framework. Gravity, as described by general relativity, continues to function as expected across the entire observable universe. Even when gravity reveals things that cannot be directly seen, such as dark matter, the logic remains consistent. Motion responds to mass. When motion cannot be explained solely by visible matter, additional mass is inferred. Gravity does not change its behavior. It exposes what is missing. In this way, gravity is both a force and a diagnostic tool, revealing the hidden structure of the universe through careful observation. At larger scales, gravity naturally combines with the expansion of the universe. It shapes structure where matter is dense and gives way to expansion where matter is sparse. This balance explains why the universe can expand, yet still maintain rich organization. Gravity remains important because it is always relevant at the local level, even as space itself expands globally. However, at the smallest scales, our understanding becomes incomplete. Gravity has yet to reconcile with the quantum descriptions that govern particles and forces at tiny scales. Efforts to unify these frameworks are ongoing, but no final theory has emerged. This gap does not undermine what is known in other areas. It simply marks the limits of current understanding. It is important to distinguish between uncertainty and inconsistency. Gravity does not behave unexpectedly at small scales. It behaves in ways not yet fully described. The absence of a complete quantum theory of gravity does not erase the success of existing theories when applied. Instead, it points to future refinement across the entire spectrum from human experience to the structure of the universe. Gravity remains continuous. There is no moment when one type of gravity gives way to another. There is no conflict between gentle environments and extreme ones. There is only scale. As mass increases, gravity becomes stronger. As distance increases, its effects spread out. As time extends, small influences accumulate into grand structures. Perspective is what makes gravity feel simple or profound. From Earth's surface, gravity is stable and familiar. From orbit, it becomes the force that governs motion. Near a black hole, it is the curvature of space-time revealed. Across the universe, it becomes architecture. No one perspective replaces another. They coexist, each accurate within its framework. Living in a version of gravity means living in a specific set of conditions. The mass, size, and composition of Earth create a gravitational environment that feels natural because it is the only condition directly experienced. Bodies have evolved in it, senses have adapted to it, and expectations have been formed around it. This does not make Earth's gravity the standard, it makes it local. Elsewhere, gravity expresses itself differently. On small moons, it hardly retains matter. Inside stars, it balances nuclear fire. Between galaxies, it governs movement across millions of light years. Near extreme objects, It alters space and time in ways that defy intuition. These differences are not evidence of inconsistency. They are evidence of the scope of gravity. Understanding gravity through perspective helps reduce the need for ultimate answers. Gravity does not converge into a single sensation or description. It expands across contexts. The important thing is not whether gravity is fully explained in every domain, but whether the existing explanations are consistent with observations and with each other. So far, they have done just that. There is a gentle reassurance in this. Gravity does not behave unexpectedly in an irrational way. When new phenomena emerge, they do so in places where conditions change, not where the rules fail. The universe remains comprehensible, even if it is not yet complete. This perspective also allows us to calmly accept uncertainty. Some questions remain open. How gravity behaves at the smallest scales is still unknown. What happens at the deepest parts of black holes is still beyond direct observation. These are not gaps to be feared. They are boundaries marking where exploration continues. For everyday life, gravity remains what it has always been. The ground supports weight. Motion feels familiar. What we've learned about gravity in other places does not change that experience. Instead, it places this experience in a broader context. The sensation of pulling downward becomes an expression of a phenomenon that operates everywhere. This awareness does not diminish the normal. It enriches it. The act of standing still becomes an engagement in a cosmic interaction. The sensation of balance becomes an alignment with space-time. The reliability of gravity becomes evidence of profound consistency, not simplicity. Living in one version of gravity means living in a set of known answers and a set of unknowns. It means experiencing gravity locally while understanding it globally. It means accepting that familiarity does not equal universality. From this perspective, gravity does not demand attention. It does not need to be fully resolved before it can be trusted. It simply operates, shaping motion, structure, and time where mass exists. The universe does not provide a single viewpoint from which gravity can be fully understood. It provides many different perspectives. Each view adds clarity without negating the others. Together, they form a coherent picture, open-ended, and still room for exploration. What remains is not a final explanation, but a direction. Gravity places everything somewhere. It connects objects without contact, structures without design, and moments without stopping. It provides a framework for change to occur calmly and predictably. Here, in the stable pull of Earth, gravity feels gentle and reliable. Elsewhere, it feels different. That difference does not scatter understanding. It completes it. Gravity operates everywhere. It just doesn't feel the same everywhere. And living in one version of it is enough to stay grounded, connected, and comfortable in a universe shaped by the same influence from one end to the other.